Okay, so this is the notes for doing a significance test for a difference of means. So it says, according to a Stanford Business article, Americans may eat fewer calories at restaurants if the calories of the food items are labeled on the menu. Okay. To investigate this, researchers compared Starbucks receipts from locations where the menus were labeled to receipts from stores where the menus were not labeled. A random sample of 30 participants, so I'm going to highlight that because that's a sample size. So 30 participants, or 30 receipts from stores with the menus labeled had an average number of 225 calories with a standard deviation of 100 calories. And then it goes on to say there's another sample of 40 receipts from stores without menus labeled that showed an average of 265 calories with a standard deviation of 75 calories. And we were asked, does this provide convincing evidence that the average calories per receipt at Starbucks with a labeled menu is less than that at a Starbucks without labeled menus? So just to go over some of the same things that we talked about last time we talked about significance tests. The first thing we need to do is we need to label the parameter. We are going to label what the statistic is. We're also going to give the two hypotheses and the significance level. So here, right, be careful your parameter is not just mu. It's going to be mu1 minus mu2. And so our parameter in this case is the true difference in mean calories per receipt at Starbucks. And you always want to indicate how we're subtracting. So we're going to do labeled minus non-labeled. Okay. Our statistic for this case is going to be x bar 1 minus x bar 2. So the mean for the labeled menus was 225 calories. And for unlabeled was 265. So that gives us a a difference in the means of negative 40. We're going to assume that our significance level is the standard 0.05, and that our hypotheses are the null hypothesis of mu1 minus mu2 being 0, in other words, being, exactly the same, not being different at all. In this case, though, we want to check, because of the way this was worded, it says, right here, it says, is the average less than without labeled menus? So that means my alternative hypothesis is going to be mu1 minus mu2 is less than 0 in this case. Because if it's less than 0, that means mu2 is bigger, which is our non-labeled. And so that's it for the state section. Then we move on to the planning step. So the name of this procedure, I think at this point you should be pretty comfortable naming the procedure. So this is a two sample t-test for mu1 minus mu2. So whatever parameter you put here should be the same as right here. And then our conditions, we always check the same three. So there's the random condition. And these are the same as if we were doing a confidence interval. So we check the 10% condition and we check the normal condition. So remember that because this is a two-sample test, a two-sample anything, you have to check the conditions for both samples. So in the little blurb above here, we know that we do have independent random samples, because in the problem it says we took a random sample of 30 receipts at first, and we took a random sample of 40 receipts So again, remember that on this section, you can't just write random and check. You need to write what it says in the problem specifically. 10% condition, 30 is less than a tenth of all receipts from labeled menus, and 40 is less than a tenth of all receipts from non-labeled menus. For a normal condition, we were not told that our populations were normal, so that means we rely on CLT. In this case, 30 is greater than or equal to 30, so that checks out, as is 40. 40 is greater than or equal to 30. So therefore, our sampling distributions of these two different samples are approximately normal by CLT. So the mean of our distribution is always going to be the null hypothesis. So for us, that means 0, that the hypotheses are the same, therefore they equal 0. And so that means we can just write that here. The general formula for a test statistic, move this up, same as before, so that is the statistic minus the value of the parameter over the standard deviation or the standard error of the statistic. Now, specifically for this, we're finding t, and so I am going to replace each of these things with their respective formulas. So for the statistic, that's x bar 1 minus x bar 2. Our parameter is mu1 minus mu2. And our standard error, so that formula will look like this. So the standard deviation of our first sample squared over the sample size of the first sample plus the second sample standard deviation squared over the second sample size. So over here, I'll actually calculate the standard deviation because there's sort of just a place for it up here. So standard error of x bar 1 minus x bar 2 is going to be equal to the square root. They told us that the two standard deviations were 100 and 75 respectively for the two samples. So we're going to do 100 squared over 30 plus 75 squared over 40. And when you put this in the calculator, you should get about 21.77. Okay, so then to do our work for our t distribution, or for our t statistic, so remember our statistic, because we wrote it up during the states section, is negative 40, minus the mean of our distribution is 0, because that's our null hypothesis, over 21.77. So that gives us a t-score of about negative 1.84, which is also, this is our test statistic, so I'm also going to put this here. Now remember that with these, the difference is that instead of drawing the normal distribution, I'm going to draw the t distribution because we're dealing with a t distribution. And so remember that a t distribution is going to look something like this. You don't want it to look normal, so you're going to leave a little bit more room in the tails, maybe not make it so high up in the middle. The middle is going to be 0. And because we're only doing less than, we're going to start at negative 1.84 and shade this area. And remember, to label it, you have to put t and then the degrees of freedom, which you might be wondering, what degrees of freedom are we supposed to use? So just like with the intervals, there's two routes you can go. You can either use the conservative estimate, so that's always going to be the smaller of the 2 degrees of freedom. So for instance, in this case, our 2 sample sizes are 30 or 40, which means our 2 respective degrees of freedom are 29 or 39. So 29 is smaller, and so I can use 29 as my degrees of freedom in this case. Now, if you remember from last time, we talked about getting the p-value. We just use TCDF in the calculator. So as far as what do you need to show, you pretty much just need to write down what the p-value is. So, but if you're wondering what do I put in the calculator, so I would go to TCDF under distributions. In this case, I would type in negative 1 million like we always do. As my lower, I would type in negative 1.84 as my upper, and 29 is my degrees of freedom. And we should get a p-value of about 0.038. Now, the other thing that you can do, you just have to be careful, is you can do, in the calculator, there's a function called 2-sample t-test. So if you remember from before, we talked about under tests, there's an option that says 2-sample t, or there's an option that says, there's an option that says 2-sample t interval, and we use that to figure out what the degrees of freedom were for our confidence intervals. So we can do the same thing by doing a 2-sample t-test. If you're on the TI-84s, that would be what option? Let me see. Because I know it's on here somewhere. Oh, that would be option 4 under stats. So stat tests, option 4 is 2-sample t-test. If you do that way, you're going to get degrees of freedom. If you do this with 2-sample t-test, it's going to tell you that the degrees of freedom are 51.78 and that the p-value is about 0.036. So I'm showing you both because depending on which way you do it, I just prefer using the conservative estimate just because it's easier, in my opinion. And I think they can tell that you're using the conservative estimate, especially if you write out like what the 2 degrees of freedom are. So this is another way to do this though. It's just if you do decide to do it this way, instead of putting 29 here, I would put the degrees of freedom from the calculator. And I would just write this this p-value here. But there's no work that you need to show in either case. You just need to have the p-value, show the work for the t-score, and draw this distribution and properly label it. When we get to the conclusion, again, just to practice writing both things, the conclusion piece is just the because blah, blah, blah is less than significance level, we reject blah, blah, blah. That's the conclusion. You always have to have that. If a problem ever asks you to interpret the p-value, that's what this first sentence I'm going to write is. So it would say something like assuming the null mu1 minus mu2 equals 0, there is a 0.038 probability, because that's what a p-value is, a probability, of getting x bar 1 minus x bar 2 equal to negative 40 or less purely by chance. Now, this isn't technically in context. If I wanted to include context, I would just say, I would write this in words. So I would just say getting a difference of means between labeled and non-labeled receipts, blah, blah, blah. You get the idea, right? This is just what the p-value represents, though. The actual conclusion that you have to have will look like this. It'll say something like because or since 0.038 is less than 0.05, we reject the null and have convincing evidence. That word convincing is important. That the average calories, I did not spell average right, average calories per receipt, I can't spell anything right, per receipt with labeled menus is less than without labeling. Now, of course, there's lots of ways to write this context. It's kind of up to you. As long as you get the right point across, you should be fine. Yeah, and so just very quickly for just important ideas, remember that for a 2-sample t-test for mu1 minus mu2, remember that your parameter is mu1 minus mu2. A lot of people on the confidence intervals hypothesis test for proportions test just kept putting p all the time, whether they were doing 1 sample or 2 sample, and you can't do that. If this is your parameter, that needs to be labeled properly. So remember, we're going to put true difference in means of whatever, and then put the order. So mu1 minus mu2. So whatever that is in context, in this case it was labeled minus non-labeled, you should always be indicating that direction of subtraction. As far as the 3 conditions, just make sure that you check all 3 for both samples. In the do section, just as a reminder, okay, I want to see the t distribution. So whatever that is, let's make it look more like a t distribution. T distribution with degrees of freedom. Your mean is always going to be 0 on a t distribution, and your critical value, your t, your standardized test statistic, whatever you want to call it, is always going to be on that axis. And just make sure that you shade the right way. If we're doing greater than, of course this wouldn't be over here, it would be over here. And of course if it's not equal to, then it's going to be both tails. So just remember that you are going to find if it's a 2-tail test, you're going to find 1 tail and then multiply it by 2 at the end. And then as far as the actual specific formula, it looks like this. It's x bar 1 minus x bar 2 minus mu1 minus mu2, which this is always going to be 0 because the null is always 0. And that's over our standard error formula, which looks something like this. I believe these formulas, at least this one, I know is on there somewhere on your formula sheet. This is not written, though, anywhere. And it is a good habit to get into of writing this out. But for the most part, this is just 4-step process like we've always done. So I hope this video helps you. If you have any questions when I get back, please let me know. And I will see y'all on, I don't know when. Thursday? Thursday. All right. Bye, guys.